Okay. Last Tuesday, I introduced the concept of equivalence when the circuit contains sources. No? Because before that, we only talked about equivalence when the circuit did not contain any sources. In fact, these were purely resistive networks. So last Tuesday, okay, meron ng mga sources yung mga circuits natin. And the first tool or the first technique that we took up with regards to this is yung source interconversion. So if you have a voltage source in series with a resistance, you can convert that to a current source in parallel with a resistance. Okay, today we're going to take up a different tool, no, that you can use on circuits with with sources. Ano? So we're going to take up Thevenin's theorem, and we're also going to take up Norton's theorem. Okay, so what is Thevenin's theorem? Okay, assume a circuit can be partitioned into two networks, A and B. So let's say I have a rather complex circuit, and I can partition this into two, into network A and to network B. And the points of interconnection between A and B are the terminals X and Y. Okay. You might think of network B as the load of network A. Okay. Now, what is Thevenin's theorem? Thevenin's theorem says that under certain conditions, and we will discuss what conditions these are, network A can be replaced by a voltage source, VTH, in series with a resistor, RTH. The voltage source VTH, we call this your Thevenin voltage. So VTH is what we call your Thevenin voltage. And RTH is what we call our Thevenin resistance. Again, no? What does Thevenin's theorem say? No? Under certain conditions, itong network A, pwede nating i-represent by a Thevenin voltage in series with a Thevenin resistance. And we call that the Thevenin equivalent of network A. Okay, what are these conditions? First of all, network A must be a linear circuit. In your future courses, you're going to be told a more formal definition of a linear circuit. But for now, let me just present you with a very simplified definition of a linear circuit. A linear circuit consists of linear sources, and then you have linear passive elements. Okay. If your circuit, if your passive elements are just resistors, capacitors, okay, we're going to take up capacitors later, and inductors, then it is a linear circuit, no? Because these are linear passive elements. Resistance, capacitance, and inductance are linear passive elements. If you have a DC, independent source, that is a linear source. No? If you have a sinusoidal independent source, that is also a linear source. Okay, so those are all linear sources. So far, the circuits that we have encountered in EEE 123, they are all linear circuits. Later on, when we talk about diodes, that's the subject matter of your second exam, then that's an example of a diode circuit is an example of a circuit that is not linear. No? Okay. But so far, yung mga pinag-aaralan nating circuits, those are all called linear circuits. Linear circuits are governed by either linear equations or linear differential equations. So that is the first criteria, that network A must be a linear circuit. Okay, what is the second criteria? The dependent sources in network A can only be controlled by voltages or currents within network A. So if this is network A, let's say this is network A. Let's say I have a dependent source here. Pagpalagay natin, I have a dependent source here. No? Let me call this K V1. No? K V1. And V1, let's say, is somewhere here. No? Yan pwede yan. No? Because this is being controlled by a quantity that is in network A. Okay. But if V1 is outside, let's say this is now network B, no? Network B. So this is connected through X and Y. If V1 is here, di pwede yan, no? This is not allowed. Again, no? Dependent sources here should be controlled by quantities inside here. And the same goes for this network B. If there are dependent sources in network B, they should only be controlled by quantities inside network B. Hindi pwedeng galing sa network A yung magko-control itong dependent source na to. So those are the conditions for using Thevenin's theorem. Are there any questions so far? Any questions so far? Okay, so again, this is network A. I'm able to replace it now with the Thevenin voltage in series with a Thevenin resistance. Okay, how do I determine these parameters? The Thevenin voltage is going to be the open circuit voltage from terminal X to terminal Y with network B removed. In other words, if I have network A, if I have network A here, let's say this is network A. Let's say this is network A. No? And this is now my terminals X and Y. So tinanggal ko, I removed network B. Okay. The open circuit voltage here, okay, VXY, whatever open circuit voltage there, that is the value of your Thevenin voltage. So yun yung ibig sabihin ng open circuit voltage. The open circuit voltage from terminal X to terminal Y with network B removed, that is the value of my Thevenin voltage. So if I had for example, if I had a voltmeter, no, let's say this is a physical circuit. If I had a voltmeter, sinukat ko itong voltaheng to, yung masusukat ko na yun ang magiging Thevenin voltage ko. Okay, what about the Thevenin resistance? Okay, let's consider only networks for the meantime that have only independent sources, no? So consider networks for the meantime that have only independent sources. So if network A contains only independent sources, walang dependent sources, then if I get the resistance looking into X and Y, so I get the equivalent resistance looking into X and Y with my independent sources suppressed, okay, with my independent sources suppressed, that is going to give me RTH. So this is going to give me RTH now. Okay. How do you suppress a source? Can I hear from you? How do you suppress a source? If it's a voltage source, what do you have to do?
Short circuit.
Yes. And if it's a current source,
Sir,
Open.
open circuit.
open circuit. Okay. So if this network contains only independent sources, and then I short circuit the voltage sources, I open circuit the current sources, kunin ko yung equivalent resistance with respect to X and Y, yun ang magiging RTH ko. Okay, having said that, let's take a very simple example. Okay, so network A has the circuit shown. So this is only network A, no? Tinanggal na muna natin yung network B. Wala muna yung network B. This is only network A. Network A has the circuit shown. Determine its Thevenin equivalent with respect to X and Y. Okay. So anong sabi natin would be the Thevenin voltage? The Thevenin voltage will actually be Vxy. If I get the voltage between X and Y here, Vxy is equal to my Thevenin voltage. What is the value of Vxy? Can somebody tell me what the value of Vxy is? So practice na rin to, no? Your circuit analysis techniques. Can somebody tell me what the value of Vxy is going to be? This is something that you can solve mentally. You can tell me over the chat box so that I can see the responses of many people. No? So ano yung value ng Vxy? Anyone? No one? No one yet? I'll give you a hint. No, I'll give you a hint. This is open circuited, and therefore there will be no voltage drop across your 10K resistance. Okay, Siri, you want to answer?
Sir, is it 20 volts?
Okay, Siri says 20 volts, no? Anybody
Oh,
else?
wait. I think 30. 30. Final answer.
30? Anybody else? May I know how you got 30 volts, Siri?
Sir, I used the voltage divider equation between the 30 kilo ohm and the 20 kilo ohm resistor.
Yeah, and why can you do that? Kasi
As you have said,
remember,
there's no voltage drop in the 10K
okay,
resistor.
okay. That's good, no? Very good. There is no current flowing through the 10K. No? Remember, this is hanging. There's no current flowing through the 10K. So for all intents and purposes, these two are in series. These two are in series because there is no current flowing here. Okay. If these two are in series, then it's easy to get the voltage across your 20K. Actually, your first answer was correct. No? It's 20 volts. No? Because, well, you're getting the voltage here, no? This is, let's say, V20K. V20K is equal to 50 multiplied by 20 over 20K plus 30K. So this is going to give me 20 volts. And because there is no voltage drop across my 10K, no, there's no voltage drop across my 10K, Vxy is just V20K, no, which is also my VTH, no, which is 20 volts. Any questions? Yes, Ruben?
Sir, why again can the 10K resistor be thought of as hanging and thus no voltage drop again?
Yeah, remember we took out network B, so this is an open circuit.
Yeah.
If that's an open circuit, that means this current is equal to 0.
Oh, right. Because it would only through the 30, then 20, then back to the voltage source.
Yeah, that means that current is equal to 0. So effectively, the 30K and the 20K are in series, and therefore you can use voltage division.
Right, right. Okay. Thanks, sir.
Okay. Any other questions? Okay, so we already solved for half of the problem. We already know the Thevenin voltage, which is 20 volts. Okay, now how do you get the Thevenin resistance? The Thevenin resistance, since this circuit, network A, is composed of only independent sources, then to get the Thevenin resistance, all you have to do is get the equivalent resistance with respect to X and Y with all of your sources suppressed. So can somebody solve that? Or can you people solve that? What is the Thevenin resistance in this case? Okay, Ruben.
Sir, with the 50-volt source suppressed, it just becomes it's shorted.
Yeah.
So with reference to X and Y, using because 30 and 20 are in parallel, you can
Okay.
put that into one resistor, which is 12K. So 10 plus 12, 22K.
Okay, that's right. No. So how did we do it? He described it in words, no, but essentially you suppress your voltage source. So you have 30K and you have 20K. No? And then now you have 10K. So looking into X and Y, you're looking R equivalent X and Y. These two are in parallel. So the parallel combination of these two will be 12K, which is in series with 10K. So RTH is now going to be equal to 22K. So what is my Thevenin equivalent? My Thevenin equivalent now is I have a 20-volt source in series with a 22K resistance. And so this is now X and Y. So what am I saying? I'm saying that this and this are equivalent. If they are equivalent, it means that if I connect something here, I connect that same thing here, that thing that I connect will not know the difference between the two. Yun ang ibig sabihin ng equivalence. Magkabit ako ng load dito, kabit ko the same load dito, yung load na yon hindi malalaman kung sino yung nakakabit sa kanya, whether it is the top circuit or the bottom circuit, because they are equivalent. Okay. Now, is this the only way to solve this problem? No, there are many ways to solve this particular problem. For example, one possible solution is we could have used source conversion. Note that I could have converted my 50 volt in series with my 30K to a current source. Right? So I'm just saying, no, this is an alternative solution. Using source conversion. No? So I convert this to a current source. So what is my current source going to be? What is the value of my current source going to be? Anyone? Did you forget already?
5/3 po.
Ano yan?
5/3 amp.
5/3, actually 5/3 milliamperes, no? Kasi K. Be careful, no? So this is going to be 5/3 milliamperes, no? And then, yung nakaseries sa kanya as a voltage source, magiging parallel sa kanya, no? So I'm going to have now 30K here. Okay. So that is the equivalent of this. So balik ko din yung 20K at saka 10K. So ito ngayon may 20K and then 10K. Okay, so this is now my X and Y. And then I can recognize that these two are in parallel, right? So the parallel combination of 30 and 20 is 12. Okay. Itong 12, together with my 5/3, I can convert again to a voltage source. The value of my voltage source would be 5/3 MA times 12K, which will give me 20. 5/3 MA times 12K would give me 20. So I'm going to get 20 volts. Okay, and then I have my 12K. And then finally, I have my 10K. So this two is now 22K. So this is now my Thevenin equivalent. Any questions? So I'm just pointing out that you could solve this in many different ways. Are there any questions? Okay, so you answer, no? VTH is 20 and RTH is 22K. Okay, Norton's theorem. So the same assumption, no? You have a network that can be partitioned into two, network A and network B, where B can be thought of as the load of A. Under certain conditions, and you're going to find out that these are the same conditions under which Thevenin's theorem can be applied, no? Okay. Under certain conditions, network A can be replaced by a current source I of N in parallel with a resistor R of N. No? I of N, this is going to be our network. This is going to be our Norton current, I of N. This is our Norton current. And R of N is going to be our Norton resistance. So instead of a voltage source in series with a resistor, you have now a current source in parallel with a resistance. So this is now going to be my network A. Now, how do I determine your Norton current and your Norton resistance? Okay, the Norton current I of N is the current that flows from X to Y if network B is replaced by a short circuit. So again, we start with network A. So this is network A. This is X and Y. I replace network B with a short circuit. And I compute for this current IXY, the current that will flow through my short circuit. This IXY is what will be my Norton current. The short circuit flowing through the short circuit current that will flow through a short connected between X and Y, no? The terminals at which network A and network B are connected. Okay, what about Rs of N? If network A contains only independent sources, Rs of N is the equivalent resistance of network A looking into terminals X and Y. In other words, Rs of N is actually equal to RTH. The same rule that we used to compute for RTH is the rule that we used to compute for Rs of N if network A contains only independent sources. So remember this is very important. Only independent sources. Okay. Any questions? Any questions? Okay. So let's go back to our very simple example. Okay. I want to determine the Norton equivalent with respect to terminals X and Y. So how do I get my Norton current? I short this. I compute for the current IXY. I's of N is equal to IXY. Any suggestion how I can compute for this current? Any suggestion? Yes, Renz.
First, sir, kunin po natin yung current talaga na ina-output ng voltage source, which is 50 divided by 30K. Tapos gamitan po natin siya ng current division, yung 20 and 10K. Yung nasa numerator po, yung 20K, and then para makuha po yung I sub XY po yung yung current
Okay,
na dumada.
I think I know what you're talking about, no? Ang suggestion mo, kunin natin tong, sorry. Ang suggestion mo, kunin natin tong current na to, no? Tama? Right? You said we can get this current, no? Let's call this I 50 volts. What is I 50 volts? Can somebody tell me? I think Renz mentioned 50 over 30K, no? Is that correct?
No po, sir, since naka-open, sir, yung X and Y, edi magiging 50 over 30 plus 20K po.
Hindi naka-open yung X and Y, naka-short, no? Naka-short. We're trying to get this current, no? So hindi siya open, it's shorted. So what is I50K? Nakuha mo yung sinasabi ko? Anybody? What is I50K? Okay, I have an answer from Adam. Adam, how did you solve it? Paano mo sinolve?
Sir, 50 volts over 30 kilo ohms. Magiging 1.67.
Well, yun din yung sabi ni Renz kanina, no? 50 over 30. But tama ba na, yeah, I think a lot of you are confused, ano? To get the current flowing through the 30K, we divide the voltage across 30K by 30K, no? But the voltage across 30K is not 50 volts. Do you see what I'm saying, Renz and Adam? No.
Yes, sir.
Oh, remember that when you use Ohm's law, this is a common mistake that I see so many times, ano? Kapag gagamit kayo ng Ohm's law, you make sure that you are using the voltage across the resistor to compute for the current through the resistor. Unfortunately, 50 volts is not the voltage across your 30K, no? So, what does sorry. So again, what is I50 volts?
Sir, is it 1.36 milliamp?
1.36. Actually, to be honest, I don't know. No? Let me compute it. No. Yes, that's right. No, who answered 1.36? Okay. I50 volts is going to be 50 divided by this total resistance.
Sir, I got the same answer as well.
Okay. Yeah. It's going to be divided by this total resistance, no? Because that is the resistance that the 50 volts sees. No? Now, what is this? The total resistance is 30K plus 20K in parallel with 10K. No? And this is going to be 1.3636 MA. Okay. Ngayon, alam na natin yung I50 volts. Ano ngayon yung IXY? Now you can use, as suggested by Renz earlier, now we can use current division. So this current will flow through two resistors that are in parallel. No? So this current will divide into two resistors in parallel. No? So what is IXY? IXY will be I 50 volts multiplied by, what will be my numerator?
20K po.
20K, no? And then the denominator will be 10K plus 20K. Okay? And I'm going to get 0.909 MA. Yes.
I have a question.
Yeah, please.
This is not about the concept, but about about the engineering notation. Does it mean that if we get an answer like this, we have to convert it to 909 microamperes?
Yeah. If we were strict, no, and a lot of handlers are strict about that engineering notation, no. If we were strict, then the answer should be 909.1, no, microamperes. That's engineering notation. Yeah. Okay.
Thank you, sir.
Okay. Now, is this the only way we could have computed for IXY? No, like I said, there are plenty other ways. No, let me just show you one other possible way. No, although there's nothing wrong with this solution. No, this is a very nice intuitive solution. No, but I could have computed for the voltage here at this node, no, with respect to ground, right? So I can apply KCL, right? I can do nodal analysis here. What is my nodal analysis here? That's going to be Vx minus 50 over 30K, okay, plus Vx over 20K plus Vx over 10K is equal to 0. Okay. So only one unknown. And if I do that, I'm going to get Vx is equal to 9.09 volts. So if I know Vx, what is IXY? IXY is just going to be Vx over 10K. So that's going to be 0.909 MA. Any question? So you could have done it that way. So which do you think is easier? Actually, there's no easier. No, it really depends on you. You can do it the way that Renz started to suggest, or you could do it using nodal analysis. I always tell my students, when all else fails, do nodal analysis, because that should be your go-to technique pag hindi na nyo alam kung anong technique ang dapat gamitin. No? When all else fails, do nodal analysis. But by all means, you can do this type of analysis. Okay, what is going to be the value of RTH? Of Rn, sorry, Rn. It's going to be the same as RTH, no? So this is an independent source, and therefore we can use the method that I mentioned. You short this, then you get the resistance looking into terminal XY, which is exactly what we did in this particular example for Thevenin, for the Thevenin equivalent. So this is going to be 22K. So finally, what is my Norton equivalent? I will now have my 0.909 MA here. I will have my 22K here. And now I have my X and Y. Any questions? Okay, let me ask you this question. If I already know the Thevenin equivalent, what is an easy way of getting the Norton equivalent?
So is it source transformation?
Yeah, you just do source transformation. Kasi alam mo na yung Thevenin equivalent. So to get the Norton equivalent, you just transform the Thevenin equivalent into a current source. And that should give you your Norton equivalent. Now, some students I've known in the past, they're not comfortable computing for short circuit current. They would rather compute for open circuit voltage. And so ang kino-compute nila is yung Thevenin equivalent, but the problem says determine the Norton equivalent. So kino-convert na lang nila yung Thevenin to Norton. So that's one way of doing it, no? But sometimes it's advantageous to get the Thevenin equivalent. Sometimes it's advantageous to get the Norton equivalent, depending on the problem that you're trying to solve. So you should, for me, you should be equally comfortable getting either the Thevenin equivalent or the Norton equivalent. Okay, any questions? Okay, so we now have this tool. We now know Thevenin's theorem. We now know Norton's theorem. How do we use it? We use it now to simplify the analysis of circuits. After all, that's what we use circuit simplification for. We want to simplify the analysis of circuits. So here's a general procedure for circuit analysis using Thevenin or Norton equivalent. The first step would be for us to remove the load. Tanggalin natin yung node, yung load. So the load in our case is network B. And then we get the Thevenin or Norton equivalent of the remaining network with respect to the load terminals. In this particular case, it's going to be network A, no? Or in our previous cases, that's going to be network A, no? So network B yung load natin, tanggalin natin yon, okay? And then kukunin natin yung Thevenin or Norton equivalent nung network A. Okay, once we have simplified network A, we now reconnect the load. We reconnect the load. And so now the circuit becomes simpler. It now becomes easier to compute for the desired quantities. So that is the general procedure for using either Thevenin or Norton equivalent. So let me jump into an example. So let's say I have this circuit. Okay. Use Thevenin's theorem. Okay, so it's specified here, no? The problem. Use Thevenin's theorem to determine I of X, the current through the 20 ohm resistor. So I want to compute for the current flowing through this resistor. So it suggests I use Thevenin's theorem. So in this particular case, what should be considered to be the load? Can someone tell me? What do we consider here to be the load? Anyone? Any guesses? Kahit na hula lang?
So is it the circuit to the right?
No,
of
no.
the
It's,
20
no, I'm
ohm?
sorry, it's not, no. What we consider now to be the load, we're interested in I of X, ano? We're interested in I of X. We want a simplified method of determining I of X. So what we should consider to be the load is this 20 ohm. Okay? In other words, you consider 20 ohms to be your load, no? Sorry about that. My iPad does funny things sometimes. No? So you consider the 20 ohm resistor to be the load. No? In other words, the 20 ohm resistor is network B. And so what do? I remove the load. No? Okay. So ano matitira pag tinanggal ko yung load? No? I have my 27-volt source. I have my 1 ohm here. I have my 4 ohm. Okay, this is now X, Y. Okay. 5 ohms, 6 amps. Okay. So what is my Thevenin voltage? My Thevenin voltage will be this one, no? Plus minus Vxy. VTH is equal to Vxy. I removed my 20 ohm. No? I removed my 20 ohm. And now I'm going to simplify this. This is now my network A. I'm going to simplify this into a Thevenin equivalent. And my strategy is, after this has been simplified, I will return the 20 ohms. And now it should be easier for me to compute for the current that will flow through that 20 ohm. So that's the overall strategy. Okay. VTH is Vxy. Any suggestions how I can compute for Vxy? Yes? Sino yung nag-raise ng hand kanina? Si Renz ulit. Any suggestions?
Sir, i-times lang po yung 6 amps and 5 ohms.
And what does that give me?
30 volts po.
Yeah, but what is 30 volts? What voltage is that? Is that Vxy?
Yes, sir, VXY.
No, that is not going to be Vxy, no? That's going to be the voltage across this 5 ohm. Diba? Kasi what you're saying is, okay, no? You have a good idea there. So this is an open circuit, no? Remember that, tinanggal natin yung 20 ohm. So itong current na to, dito lang iikot siya, no? Right? So if I multiply this 6 ohms by this 5 ohms, I'm going to manage to get the voltage across this 5 ohm resistor. But that is not Vxy. Yes, Ruben?
Sir, following up on what Ren said, I think that's half of it solved, because that would be the voltage at node Y. So because that's the voltage, just a guess, sir. Because that's the voltage there, if we solve for the voltage on where node X, that should get us Vxy then.
That's right, no? That's right. Vxy is just Vx minus Vy. No?
Yeah.
And the voltage at node X with respect to let's say this reference minus the voltage at node Y with respect to this reference would give us Vxy. Now, you mentioned that Vy is what? You have to tweak the answer of Renz a little bit, no? Is it 30 volts? Okay, be careful of the polarity, no? Because this 6 amperes will be flowing through the 5 ohms from down to up.
Oh, so it's negative 30.
So this is going to be 30 volts. No? So Vy is actually negative 30 volts.
Oh, okay, yes, sir.
So what is Vx? So you have half of the problem solved. What is Vx? Anyone? Iba naman, ano? I've been hearing Renz. Thank you very much, Renz, no, for trying to answer all the time. No? Can I hear from somebody else? No, what is VX? Somebody has an answer. Lore, can you explain why 21.6 volts?
Sir, since the 27 volts, 1 ohm and 4 ohms are in series, we can compute for the current. And after finding the current, we can find the voltage across 1 ohm, then subtract it by 27 volts. We get voltage at node X.
Yeah, okay. Yeah, that's one way of doing it, ano? Actually, if you know the current, you multiply it by 4 ohms, that's already the voltage, right? So you don't have to do the subtraction anymore.
Okay.
Kasi, di ba, alam mo na yung current, di ba? So, pag alam mo yung current, you multiply the current by 4 ohms, yun na rin yung voltage. No? But you yourself said, no, these are in series. So what is the shortcut that we usually use when you have series resistors?
Voltage division.
You could use voltage divider, di ba? So anyway, those are all valid, no? Yung valid yung procedure mo, yung sinabi kong alternative valid din, voltage divider valid din. No? If we use voltage divider, what's our formula? No? Vx is 27 multiplied by 4 over 5. And ano yung sagot? What was the answer that you gave?
21.6 volts.
Tama ba? 21.6? Let me just very quickly check. No?
Yes, sir. I got the same answer as well.
Okay, so I will take your word for it. No?
Same as well po.
So this is 21.6 volts. So finally, what is VTH? VTH is just now 21.6 minus negative 30. So you're going to get 51.6 volts. Okay, so that's VTH. Okay, what about RTH? I'll let you compute for RTH. What did we say we have to do? Okay, first of all, we can use the method that we discussed because our sources are independent sources. No? So what do we have to do? We have to suppress the sources and then get the resistance looking into terminals X and Y. So can somebody tell me what the value of RTH is going to be? Anyone? Those of you that want to put their
Sir, can you
answers.
switch back to the previous slide so we can see the individual resistances?
Okay, there.
Sir, will it be
I have
5 plus 5 equals 10?
I already have one correct answer among those that answered the chat, no? So let me draw the equivalent circuit. I think if I draw the equivalent circuit, it should be clearer, no? So this is 1 ohm, 4 ohms. So the voltage source becomes a short circuit. This is X, this is Y. And then I have the 5 ohms here. And then this is an open circuit. And so I'm if I get an ohmmeter and I connect my ohmmeter across X and Y, what resistance will I measure? Okay, so this is RTH. Okay. The answer is 5.8 ohms. Let me see how many people got it. No. Okay, why 5.8? These two are in parallel. No? The parallel combination of these two is 0.8 ohms. Product over sum. No? So 4 over 5, that's 0.8 ohms. And that is in series with your 5 ohms. So you get 5.8 ohms. Okay. So yes, no? So many people see that. So what is now my Thevenin equivalent? My Thevenin equivalent now is, I have my 51.6 volts. And then I have my 5.8 ohms. This is now X and Y. No? But what was our original problem? Original problem is to get the value of this current. So what do we have to do? We should reconnect now the 20 ohms. So this is reconnect. You reconnect now the 20 ohms. And whatever current that flows through that would be the answer to my problem. That would be I of X. That would be this current. So now you see how trivial it is to compute for I of X. What would I of X be? I of X will now just be simply equal to 51.6 volts. That is my total voltage divided by my total resistance, no? Divided by 25.8 ohms, which is 2 amperes. Any questions? Okay, why are 1 and 4 in parallel? Okay, let's take a look at 1 and 4. No, the two are interconnected here at that one end here, and the two are also interconnected at the other end, and therefore they are in parallel. Did that answer the question? Who was the one that asked? Si Ruben? Okay. So again, no, you're going to have to hone yourself in detecting what are in series and what are in parallel. Yeah, Romeo, may tanong ka?
Yes po, sir. Medyo unrelated po dun sa problem, pero curious question lang po regarding the 5 ohm resistor.
Oh,
What if po yung kaparallel niya po instead na open circuit, shorted, sir? Would that
shorted?
affect the equivalent resistance?
Yes, of course. No. What is a short circuit in parallel with any
Zero.
resistance?
Would that be zero, sir? Zero.
Yeah, no.
Ah,
Because a short circuit has zero resistance, di ba?
Yes.
So if you get the product over the sum, magiging zero yon,
yes,
no?
yes, sir.
So
And
that will
just to
affect
confirm.
it.
Thank you, sir. Thank you.
Okay. Any other questions? Okay. Sabihin natin na hindi natin ginawa yung kanina, no? Hindi natin ginawa yung problem kanina. And ito ngayon yung problem. The same circuit, pero ang technique na pinapagamit is Norton's theorem. Okay? Kasi alam na natin yung Thevenin's theorem, so madali natin makukuha yung Norton's using source conversion. But let's say we didn't do that, and the problem here states that you're supposed to use Norton's theorem to determine I of X. So again, you use the same strategy, no? So the first step is to remove the load, no? So you remove the load. So you have your 27 volt, your 1 ohm, 4 ohms. So ito yung X, ito yung Y. 5 ohms. And then your 6 amperes, no? Now we're supposed to use Norton's theorem. So the first step is to determine I's of n. How do we determine I's of n? What are we supposed to do? What are we supposed to do? Can I ask somebody at random? Let me hear from other people, no? What about Unrel, no? Are you around, Unrel? Ano kailangan gawin para compute yung I's of n? Unrel, are you around?
Yes, sir.
So anong kailangan gawin para compute yung I's of n?
We'll have to get the current of I sub X and Y, sir.
Paano, sorry?
Yung like paano ba explain?
Ano ilalagay natin between X and Y?
We'll have to short it, sir.
Exactly, no? So you have to short X and Y. And then titignan natin kung ano yung current na magfo-flow dun sa short na yun, IXY. And that would be I's of n. Okay? So kanina, when we were using Thevenin equivalent, when we needed to get the Thevenin equivalent, we opened it and then we got the open circuit voltage. Now we short it and we get the short circuit current. Okay, how do I compute for IXY? Can I have a suggestion? Let's hear a suggestion from you and then let's proceed in that manner. Can somebody suggest a method? Let's hear from Ram. Are you around? Can you suggest a way of computing for IXY?
I'm not sure, sir. KCL po, is that applicable?
Yeah, you mean nodal analysis?
Yes po.
Nodal analysis is always applicable. Where will we apply KCL? What node?
Node X po.
Okay. Sige, let me follow your reasoning, no? You brought up an interesting way of doing this. Note that this whole thing is just one node. Okay, that whole thing is just one node. So let's say, let me call that node. Well, you called it node X, ano? Sige, let's call it. Let's say that that's node X. Okay, so that has a voltage V of X. So what is my nodal equation? Ram, can you continue? What will my nodal equation be? Are you having difficulty?
Only, sir.
Anyone? What is the nodal equation going to be? Let's see.
Hello po. Tinig po ba?
Sige, Romeo, what is the nodal equation going to be?
Sir, Vx minus 27.
Vx minus 27
Vx over 4.
plus Vx over 1, ano? Over 1.
Yes, sir. Over.
Okay. But that's okay, no? Vx minus 27 plus Vx over 4
Plus Vx over 5.
plus Vx over 5
Minus 6.
minus
Plus
6.
6.
Okay, plus 6 is equal to 0. Okay. So, tama yon, no? Okay, so I can compute for Vx. I have that somewhere here. Yeah. I can compute for Vx, and Vx is going to give me 14.48 volts. I already have it somewhere here. Okay, but what I'm interested in is IXY. So if I know Vx, how do I compute for IXY? Anyone?
Sir, do we just add the current through the 5 ohm resistor and the 6 amperes?
Yes, you can do that. No? In other words, you can apply KCL to this particular node. No? Okay. In other words, you now break it up again into two, because these are two nodes essentially. Ano? Well, this is only one node, ano? But you can actually have subnodes. No? This is one subnode. This is another subnode. So you can apply KCL to this particular subnode. No? So if we do that, what is our equation for IXY? Sige, naumpisahan mo na. What will that be? Who was the one that answered? Sorry, I lost. Sino yung sumagot kanina?
Ako po, sir. Sorry po.
Okay. So what is my expression for IXY?
That will be Vx over 5 ohms plus 6 amperes.
Vx over 5 plus 6. Okay. Good, no? So that's applying KCL here, no? I could also have applied KCL here. Right? I could also have applied KCL. Vx minus 27 over 1, okay, plus Vx over, baliktad pala, no? 27 minus Vx over 1 minus Vx over 4 should be equal to IXY. So you should get the same answer. No? Anyway, if you compute for IXY, okay, what is that? What is that going to be? That's going to be 8. I have the figure already. That's going to be 8.90 amperes. Okay. Okay, so finally, what is my Norton equivalent? Okay, I have my 8.9 amperes. And then my Norton resistance would be the same as my Thevenin resistance, which we already computed for, which is 5.8 ohms. No? So now this is now my X and Y.
Sir, I have a question.
Yes, I'll go ahead.
Is it possible to use superposition since there are two independent sources?
Yes, by all means, you can. This is to compute for what? For
IXY.
yeah, but in this particular circuit, you mean?
Yes, sir.
Yeah, you can. So you can consider the 27-volt acting alone, then you can consider the 6 amperes acting alone, and then you can just add the two up to determine IXY. You could have done that. So you can try doing that too as an exercise. Okay. So anyway, so this is now my Norton equivalent. But remember, I'm interested in this. No? So what do I have to do? I reconnect now my 20 ohms. Okay. And this will now be I of X. Now what can I use to determine I of X?
Current divider, sir.
Yeah. Now you have a current divider. No? So you have I of X is equal to 8.9 multiplied by 5.8 divided by 25.8. No? And this should give you 2 amperes. The same answer as when we had used Thevenin's equivalent. So we had some suggestions of how to compute for IXY. Okay, the first suggestion was nodal analysis. There's a second suggestion using superposition. Can you think of other ways? We could also have used source conversion, right? I could have converted this to a current source. Okay. And then I would have these two in parallel. And then I can convert now that back into a voltage source. Then I can also convert this to a voltage source. And then now I have a single loop circuit and I can compute for IXY. Do you see that? Nakikita ba niyo yun? If I went too fast, I convert this to a current source. No. And then this will be in parallel. So I put the parallel together. Then I convert it back to a voltage source. And then this one I convert to a voltage source. Then I'm going to end up with just a single loop circuit, and I can easily compute for IXY. And if you check, itong Norton equivalent should be the current source equivalent of this Thevenin equivalent. In other words, 51.6 divided by 5.8 should give me 8.9. No? Should give me 8.9. Any questions? Any questions? Okay, let's go back to determining RTH. So we said that when your network, we're talking about network A, when your network A contains only independent sources, then madaling kunin yung RTH. We just suppress the independent sources and then we get the equivalent resistance looking into the terminals, not the terminals of interest. But what if network A contains dependent sources? Kapag ganon, di na natin pwedeng gamitin yung method na yon. We will no longer be able to use that method of getting the equivalent resistance. There are other methods that we now have to use. And that's what I intend to take up in our next meeting. The other methods of determining RTH. Okay, so that is all that I want to present this afternoon. Are there any questions? Any questions? Okay. Yes, Will. Sorry, Ren pala. Renz.
Sir, yung tungkol po sir kanina, you said sir na kapag may dependent source, what if sir yung dependent source is controlled lang din naman siya within the network? Is it possible to still use Thevenin's and Norton's theorem?
Yung network A, can contain independent and dependent sources. The only rule is yung dependent source must be controlled by a quantity also inside network A. Now that you can still get a Thevenin equivalent, pero yung method na pagkuha ng RTH na pinag-aralan natin today, hindi pwedeng gamitin.
Okay, sir.
May ibang method na gagamitin para kunin yung RTH. And yun yung kukunin natin yun yung kukunin natin next week.
Okay po sir. Thank you po.
Okay. Any other question? Okay. Anyway, like I said, that's all I prepared for now. I was considering continuing, but since a lot of students have difficulty with Thevenin and Norton, I wanted to take it slowly. That's why I decided not to press on with other methods of computing for RTH now. So what I want you to do is, okay, you practice now. Kailangan practice kayo, and then hopefully on Tuesday you would have practiced enough, and then we can move on to yung mga mas mahirap nga na method for determining RTH. Okay, I will, if you want to leave, you may leave already. I will keep the session open until the last person leaves, so that in case somebody still wants to ask any questions, I will still be here to answer. So that's all. Happy weekend na lang sa inyo lahat.
Thank you, sir.
Thank you, sir.
Thank you,
You're
sir.
welcome.
Thank you,
Thank
sir.
you po.